You can start. Just
Okay, so today I'm going to talk about a search engine I built for Lean. It's called LeanExplore, and it's a semantic search engine for Lean 4 mathematical libraries. I'm Justin Asher. I'm a researcher right now, or a resident working at Axiom Math, and this is some work that I did before being at Axiom. Okay. Okay, so this talk is going to have four parts to it. The first part is I'm going to detail what is difficult about doing search in Lean 4 libraries. The second part, I'll talk about the underlying search algorithm behind LeanExplore. The third part, I'll talk about the applications and then the conclusion. So the thing that's really hard about finding declarations in Lean 4 libraries is that it's kind of like a chicken and the egg problem where like if you're getting into learning Lean and you need to find something and you go to the MATLAB documentation, a lot of the times you'd have to know at least the name or the similar names of the things that you're looking for. And it's hard you can't really search for things semantically. So the goal behind building LeanExplore was to build a system in which people can find things both formally, informally, by name, or by docstring. So right now there's around 112,000 declarations in MATLAB. There's around 230,000 theorems, and then we also have other packages available like Fizzling's batteries, the standard library, which we were just talking about, and more. So the existing search interfaces they're quite difficult to navigate, and I wanted to create something that was a lot easier to use. They lack the ability to search for things both formally and informally by name, and so I was like, instead of just indexing one thing, because a lot of the existing search engines, for example, they only choose to index by one data type. So Lean Search will index by informal names or informal descriptions. And then the MATLAB docs will use a system where you can search over the formal names, and other ones will search over types. And my goal was to index all of that data into one place under one roof. Okay. So the approach that I used to build LeanExplore is I started by inductively informalizing all of the Lean top-level declarations. So these are theorems, definitions, structures, lemmas, and more. And then I use an LM with a dependency context for consistency to informalize these, meaning we generate informal English descriptions of the formal statements. And then we create embeddings for each declaration. So most search engines would only create one embedding, which would be maybe an informalization embedding or maybe an embedding over the formal code. In this case, I created four of them. One for the name of the statement, one for the source code, one for the docstring, and one for the informalization. And this allows you to be able to search over all of these fields to quickly access Lean 4 declarations. I added all these to an embedded unified index using an inverted file system in BM25 Plus along with PageRank. And then I used a hybrid search algorithm to combine all of these signals into one place to help give the most consistent results. Is there any questions before I go on? Okay. Okay. So let me discuss the search algorithm behind LeanExplore. So the search algorithm, I wanted to build something that you can run locally. So what that means is that if you choose a relatively large embedding model, it might not run on everybody's laptops or local machines. So I chose to use a smaller 109 million parameter embedding model. An embedding model is a model which takes some sort of um, text in English and it produces a vector from it. So this vector represents in space where that text, what that text means semantically, and then you can map vectors which are in similar spaces in space, have similar semantic meanings. And so when you search for something, it embeds the text, the informal text, into an embedding vector, and then we can find the similar statements in the Lean library based off what vectors are near our embedding vector. So this model is lightweight, but it was relatively effective for mathematical content. The problem I had with this model was that it it seemed to miss a lot of, and this was a relatively common trend among these embedding models, is that they weren't very good at distinguishing between things that had very precise meaning. So when you look up something and you look up a theorem and you look up that theorem in a specific case, the embedding model wouldn't really know what you're looking for. And this was relatively consistent. So on top of that, I used a BM25 plus search algorithm. And so the BM25 plus search algorithm basically is it's a keyword search algorithm that means that when you search for something like a group or a ring or something in Lean, it can distinguish between what those things means. And so this handles the exact term relevance that the underlying embeddings might miss. And then I also computed PageRank. So PageRank is the algorithm that made Google famous, for example. And so the thesis there was that if a lean statement, um, if it's very relevant and it's what the user is looking for, it's likely that the page rank is going to be a higher score. So if you look up the fundamental theorem of calculus in the Lean library, you're going to be hit with a lot of different versions of it. Very simple versions, versions from, that are from like functional analysis or over different spaces. And the naive Lean user is probably just looking for the most basic version of the fundamental theorem of calculus. So in order to distinguish between all these different versions that show up, I added a relevancy score based off of their citation count, which is PageRank. And so this is a score which, if something's cited more often or it has more graphical relevance, meaning it's more central among all the statements in Lean, it'll have a higher PageRank score. So I weighted these three signals. I gave 1 point times the semantic score, plus 1 point times the BM25 plus score, and 2.2 points times the PageRank score. And I took the sum of these three factors, and the semantic score is here the max score over the name docstring, the informal statement, and or in the informal statement. Okay, I hope that makes sense. Okay, so there was one problem I incurred, which was that when I was extracting data in Lean, so I was actually extracting data from the compiled files, which maybe it's probably better to write a parser on the info tree in Lean. But when you write something in Lean, you actually get multiple constants that are generated from a single statement. So here's an example, is that when we define a scheme in Lean, which is a structure that's extends a locally ring space, you get the constant, you get the underlying inductive type, which is the scheme. You get the constructor, which is when you try and make a scheme. By the way, a structure is an inductive type with one element for those who are familiar with Lean. You get constructor, you get the local affine theorem, which is how you define a scheme locally, and you get the projection down to locally ring spaces and so on. And so when I got all this data, I wanted to bundle it into one place to compute, because like if I'm computing PageRank, I don't really care about the page rank of, for example, the constructor. I care about the page rank of this underlying Lean statement. So I wanted to bundle all this information in one place. And so I mapped all of these up to this underlying source text to give the user the ability to search over source text and being able, instead of being able to search over constants. Because the source text is typically, I think, more intuitive, or at least the elaborated type is more intuitive to the user than like, the generated constants. Okay. So then we generate informalizations from these extracted data. And so the goal was to translate Lean 4 statements into concise, informal English descriptions suitable for mathematical textbooks. So I gave the model access to the formal statement, the docstring if it was available. I focused on the core mathematical concepts. I told it not to write using Lean. So models right now, when they write, if they try and translate Lean informally, they have a habit of just putting a bunch of Lean code in that informal translation. And that's not very helpful for somebody who's trying to search, because somebody's trying to search for things is probably going to just want to know what it means in English. I told you standard mathematical terminology to be brief. And so I gave it all the relevant context, and I also gave it all the dependencies. So I inductively informalized, meaning I start with the base axioms and we go up. And this means that our informalizations end up being very accurate. And I was very trusting of the resulting informalizations because there was very little room for error. Um, and I'm sure you could just have a system where you just ask it to informalize each statement individually without providing the dependencies informaalized first. But it has the chance of introducing error into your system, and we want to minimize the amount of error when we're translating things and searching over it. So oh yeah, and here's an example, is I was also going to mention that with BM25 plus, here's an example of why I used it. So if you look up a finite morphism of schemes by just using embedding model, what you end up finding is that out of the first 5 results, it's like, okay, well, this one's talking about a finite morphism of schemes. This is talking about a rational map. This is talking about a partial map. This one's actually talking about a finite morphism scheme. And this one is talking about composition of morphisms. So only 2 of these are actually like relevant to maybe what the user is looking for. But when you use a hybrid search algorithm, what I ended up finding was that out of the first 5 things that the user retrieves, all 5 of them were actually relevant to their query. And this was, I think, very important because I think that if somebody's looking for something very specific in MATLAB, I'd rather have the search algorithm be kind of over precise and too precise based off of these factors so that you can find very specific statements instead of having to wade through a lot of declarations. Okay, so the search algorithm is just you take the user query, you embed it, you do a inverted file index, which is, I don't need against that, semantic filter, get our three signals, normalize the scores. So I normalized all of them. So all the scores were relative to the other statements that we're retrieving. I combined them, sorted them, and returned them. Okay. So I tested this against other search engines. So I took 300 AI-generated queries reflecting typical like MATLAB search tasks, so things you might be looking for. You know, the fundamental theorem of calculus, fundamental theorem of algebra, definition of a scheme, and other things. And I tested against two leading search engines. One of them is LeanSearch, and another one was Moogle. And I used an LM judge to evaluate whether or not the results generated by LeanExplore were in fact better than these other search engines. So that means is I gave it each of these search results. I gave it the top five results from each engine presented to the evaluator, and the model was then asked, out of these three search engines, how would you rank them? Which is the best search results? Which is the second best, and which is the worst? I allowed for ties to take place. Um, and we asked it to find it based on the accuracy and the relevance from the natural language query. And I did this over three independent runs to ensure that there was some reliability because these models, even though they're intelligent, there's entropy. And this is something interesting to think about is when you're using LM Judge for tests like this, I know it does have some level of entropy to its responses, meaning sometimes it would rank things just completely differently. So you have to do it over multiple runs. And so the competitors for LeanSearch, which was using a 7 billion parameter E5 Mistral model, and Moogle, which is a semantic search engine for MATLAB. And I don't know what type of model they're using. And this is, I think, a little bit older than LeanSearch, so I think it's a little bit outdated now. So out of the results that I found that 55% of the time LeanExplore came in first place. So it outscored LeanSearch and Moogle. And it came in third place only 10% of the time, which I was really happy about because that meant that if you're trying to find something in Lean, out of all the search engines, you were least likely to not like to have the worst search experience. In fact, that was half of the time, half the percentage of the time that LeanExplore came in third place. And I think this is quite important. And I also did a head-to-head comparison. So versus LeanSearch, LeanExplore comes in first place 50% of the time. The competitor wins 40% of the time, and it ties 10% of the time. And versus Moogle, it was even more extreme, where it was 80% of the time. So it very rarely came in last. I achieved this with a lightweight model, and this is like about 70 times smaller than LeanSearch's model. So the fact that we're getting better results using a much smaller model was like really, really nice because this is something that people could just use locally. Um, is there any questions?
And did you actually look at the results, or was it only your AI looking at the results?
Yeah, so I looked through the results. Well, I can talk about this next, but the main thing is that, yeah, so I looked through the results, and I think the biggest thing that the LeanExplore search algorithm struggled with was that if you type in a query, and your query was something very vague, like you're just looking for vector space axioms. Since I was using a smaller model, it was less likely to give you a good result because it doesn't maybe as well understand what vector space axioms were. But um, yeah, so on the other hand, it did tend to be much more accurate when you were looking for very specific theorems or very specific statements in MATLAB. Okay. Anything else or any other questions about the algorithm or?
I have a question about your evaluation. Which version of MATLAB did you test this against?
That is a really good question. So this was on version 4.19. Which is a little bit outdated now. That was the current version back when I tested this. And I think that is in particular why Moogle did so bad is because I think Moogle was the database that Moogle was using is even more outdated. I think it was, I think it's an older version of Lean. So I think in that case, some of the queries weren't showing up properly, but I also still think it did provide better results. Any other questions about the algorithm or the evaluation or anything? Okay. So the problems with the algorithm was that it could miss very broad queries. it could be very oversensitive to variable names. And so this is a really big problem with these lean search algorithms, or in general, anything related to math search, is that if you search for something and it says, um, you know, the sum over X, and then you also look at that same thing, sum over Y, it's not going to show up as well. And this is exacerbated by the BM25 plus algorithm, where it would work really well if you search for things informally. But when you start searching for things using specific variable names, these models would struggle, indicating that we need to use some kind of variable indifferent search algorithm, which we are not doing right now and would require a bit of engineering to do. Page rank bias was also a problem. So sometimes certain statements would be very foundational to a lot of other statements, but they wouldn't always be very relevant to what the user is looking for. So occasionally you would have these statements pop up where it wasn't exactly what you're looking for, but also wasn't a really big deal because then the next query would be very relevant anyways. We only have limited coverage at the moment, so it only indexes batteries, init, lean, mathlib, physleans, and standard. We need broader ecosystem coverage for a search engine like this to take place, and there's no nightly updates. So currently, since I can't work on this, the data is becoming outdated as the libraries evolve, and hopefully this is something at some point will get resolved. Okay. So I want to talk more about the applications behind this and why did I build this? Because I didn't just build the search algorithm for the sake of having some state-of-the-art search algorithm. In fact, that was less of my concerns. More of my concerns was creating something which is accessible, meaning that everybody could use this very easily, and something which can also integrate with AI applications. Okay, so there's 4 different ways that you can use LeanExplore. One of them is through the web interface at leanexplore.com. And this gives you nice features like dependency exploration, API key management, tracking your history, and providing all the nice data in one place. I also created a command line interface, which was just if you're using the command line and you want to look up things, you can use it that way. I have a Python library, so you can do pip install LeanExplore, and then you can get the database off of the cloud. So you can download the whole LeanExplore database locally, and you can run it locally. And you can also use this with the Model Context Protocol, which is a protocol that AI agents can access these databases and allow them to use it, which is like extremely important. And I'll explain why in a minute. So the web interface demo is like if you look up the square root of a real number. Okay, so you look up the square root of a number, and first off, you notice you can search by packages. So if you click on the packages, then you can choose any of the packages I mentioned earlier if you want to do this in mathlib or if you want to do this in another library. When you do so, you're going to be hit with something that looks like this. It's going to give you real.square root, and it's going to tell you what file it is. If you click on the real.square root, this is going to take you to the documentation page for it. So this is going to take you to the mathlib documentation. And if you click on the link, this is going to take you to the source location or the source code position of this lean declaration. Then you can see the lean code. So you can see it's a non-computable definition of a square root. It's for X and R, and here's the definition. It gives you the doc string. So the doc string tells you this is the square root of a number. It returns 0 for negative inputs. And it also gives you a Gemini 2.0 flash translation. And the reason this is really important is you would say, well, we have the doc string. Why do we need the flash translation? But in a lot of cases, the doc string is either incomplete or it doesn't contain all the information that we're looking for. So the flash translation bridges that gap and allows the user to quickly understand what these formal statements mean informally. And I also added a little button right here that clicks Find Similar. So that if you take this Gemini 2.0 flash translation and you click Find Similar, it'll find statements that are semantically similar informally to this statement, which is very helpful. And then you can click on the Find Dependencies graph so that if you're looking at this and you say, well, what is natural number real.square root? Well, you can go here and you can say, oh, here it is, natural number real.square root, and you click on it and it'll bring it up for you and you can see, okay, this is what this means, and you can exit when you're done looking at this dependency. And so this gives you a quick way to navigate through all these Lean4 declarations. And then I also have on the website an API key system. So the API works in the way that if you want to run LeanExplore locally, or if you want to integrate it with the Model Context Protocol for AI agents, you can go online, grab an API key. You don't have to download the database yourself, and you can just export that locally on your local machine, and you can use the search engine that way. Okay, so one of the big applications, okay, so the big reason I was interested in building something like this is because of this thing called the Model Context Protocol. And so what the Model Context Protocol does is it means that if you have an AI agent or you have some sort of AI system, you can start hooking up external tools to it. So previously, that might be like a Python environment. You could hook up a Lean environment to an AI system, and you could say, here is, you're going to edit this Lean file, and you're going to have a tool which is going to, allow you to run the file or get feedback on the file, or you can run Lean code in space or in your, you can write Lean code and you can run it. You can get diagnostics and whatnot. So it allows AI agents to use specialized tools during conversations. And AI can query real-time information from connected services. So in this case, so typically in other cases, like you might have some databases, a Postgres database, GitHub, Slack, or something, and you want to integrate that into your AI system. And the Model Context Protocol gives you a really nice interface that goes between your AI models like Claude, ChatGPT, Claude Code, anything that can use the Model Context Protocol, and your underlying database and also your tools. So it's a nice way of accessing databases. And in this case, our database is going to be LeanExplore. And so it's going to be a way for us to search these this Lean interface using, or it's going to allow an AI system to use this Lean interface. Okay, so for LeanExplore, there's three main tools that I gave the AI. I gave it the ability to search. So this meant they can semantically search things. And when it semantically searched for something, you could also get the dependencies. So this would tell you what are all the statements that this thing is dependent on. And then it would also be able to get by ID. And what this means is that when it got the dependencies, it would return a list of the state or the names of all the dependencies and would also return their IDs so that the AI system could then grab some of those dependencies by their ID and understand what they mean and what they represent. So using these three tools, an AI system, it could help an AI write Lean code. Okay, so let me give you an example. And this is something that like, I know a lot of people started using this. And so a lot of people started using this when they're like using Claude Code or something. And Claude Code wanted to write, if you're writing a Lean file, you might try just like asking Claude Code, like, can you fill out this Lean declaration or something? Like, can you fill out this theorem, write the proof? I've already formalized it. I just need you to go through and write the proof. And Claude would say, okay, I'll try and write it. But then it would constantly be like, okay, I don't know how this is defined in Lean. I don't know how this other, definition I want to use or this other theorem I want to use to find. And so it would really struggle. And so essentially the point of this was to bridge that gap. So you search for this and it says I searched how is a group I searched how a group is defined in Lean 4 and it goes so the user is asking about how a group is defined in Lean 4. This is a specific question about the Lean theorem prover in its mathematical library. I should search for informal information about group definition in Lean 4 using the LeanExplore tool to find actual definitions and structure. And so then it goes, let me search for a group in the Lean database to see how groups are defined. And so when it searches for that, it'll help understand how a group defined by searching through the mathematical library. And it would look up its query to group. It would choose all the packages, so it wouldn't filter by any packages. And then it would get its results back. And it would, it'd have results. The first ID is 8438, and the declaration is the group. Okay, so that's probably what we're looking for. And it goes, perfect. Now they have the core definition of a group in Lean 4. Let me also look at what a div-inv monoid is, since the group extends it. So in the definition of a group, it extends a division invertible monoid, I guess is what that probably means, or I'm guessing. And I should search for that to give a complete picture. And so then it would search for that as well. And it would say, okay, let me find the first five results. Let me look up the divisible invertible monoid. And it would go, okay, now I have a good understanding of how groups are defined in Lean 4. Let me also check what a monoid is, because this thing would extend a monoid. So then it also looks up what that is, and it finds what a monoid is. And it goes, great, now I have a complete picture of how a group is defined in Lean 4. Let me explain the hierarchical structure, where it's a monoid, it extends a division with inverse operation and division plus integer powers, and then that extends a group. This is a nice hierarchical design that builds up the structure step by step. And then it returns something like this to the user, where it would say, a group in Lean 4 is defined as a class that extends a division inverted monoid with one additional axiom. And so it gives the definition of a group, and then it would say, okay, extends this thing where this is the additional axiom that we're using, and it would explain what this means. And it explained the key axiom here. But what's nice about this is since the AI system wasn't just returning the definition, it was also looking at the dependencies, it could then tell you the definition follows the following hierarchy: semigroup, monoid, division inverted, monoid to group, and it explains what each of the building blocks means. And then it also tells you other things. So it's like, okay, well, it's looked through a lot of information for you. It's not just giving you a top result like a naive first approximation. It's actually going to tell you more about how the other types of groups are defined or how other ways you could define a group in MathLib. So it also talks about how you can have left axioms and right axioms to define group structures with minimal proof obligations, allowing you to prove, or it gives you these properties, I guess. So allowing you to prove either left or right cancellation and have other properties derived automatically. So this kind of like AI search system, which I was not able to host this on the internet because it would get really expensive for me. Like I'm just hosting this on a relatively small node, but this AI system is like really, really useful. So if you get an API key and you just integrate it with Cloud Code it, I think it makes it a lot easier to learn about Lean for, you know, anybody, somebody starting out and somebody who wants to learn more. Okay, so I guess I'm about done. Sorry, it's kind of a short talk. I'd be happy to answer any questions. But so I'm starting to get growing community adoption in the Lean community. So I'm getting around 250 to 500 search requests per day, and I have more than 100 registered users now. I know that people have started using this for various AI applications as well. So like I get people who are, you know, applying this to automatically prove statements so that if you can just let Cloud Code or Codex or somebody run in the background. I'm getting this so that if, yeah, and then people who are like doing draft sketch prove and different hammering techniques and whatnot, they're also using this. And so this is, yeah, this is all things that I know people are doing. Yeah, and so this is the website. Here's the documentation, and you can try it at pip install LeanExplore, and that's my email. Any questions?
Yeah, so
Thank you.
questions?
Yeah. How practical would it be to update the libraries nightly? You said it's stuck on 4.19. Like, would it
Yeah.
a lot of
Yeah,
money?
sorry.
Would it take a lot of time?
So I don't think this would take a lot of time. I just like when I wrote this, I was not very good at writing Lean code. So I, you know, I did the naive thing. And then I think, yeah, there's definitely ways you could update the libraries nightly. So out of publicly available things I know about, Auguste Parou had a system where he was building on top of the Lean REPL, and his system essentially can do file by file data extraction. And so using that branch of Lean REPL, you could create a search engine that you could update in real time, assuming the Lean REPL is kept up to date. However, I was trying to integrate that, but I never ended up integrating it because that would require like refactoring and reworking the entire underlying database structure. And I didn't want to have to like redo the schemas and everything, if that makes sense. So yeah, it's certainly feasible. And you would just need like, you just need a well-written Lean data extraction system.
Thank you.
More questions? Yes.
So one thing that I guess maybe more power user or advanced user of these search tools do is often not just kind of keyword search, but searching for a kind of particular pattern, like, oh, I want to look like something that has this particular sub-formula in it or things like that. At least in Rock, this is something that I do quite a lot. And I feel like these sort of kind of more semantic search system are not really well tailored for that. And I was wondering whether it's kind of just two different sorts of tools that maybe should coexist, or whether there's a chance of having kind of these two in the same system, or like whether you have thoughts about this.
Yeah, so I guess my opinion on that would be that one of the goals of when I was building LeanExplore was to combine multiple search signals. And overall, I think ideally when we're interfacing with these formal libraries is we're going to want just one search interface where you can search over multiple tools. I don't know if the right way to do that is by having some sort of router, which route requests to the right tools. Or, you know, I don't know. Like, I agree though that like, I think there's a lot of fragmentation in the way that you can search over Lean libraries right now or over formal libraries. And I think LeanExplore was starting to close a bit of that gap, but I still think that there is a fairly long ways to go to get to the point where that is no longer a problem. Yeah, I don't know. I think like a really good embedding model though. So that could be something that could help.
When you describe also exist. This is what is called Loogle that was mentioned.
Yes, okay.
Yeah. Any other questions?
No more questions? Okay, well, so thank you very much, Justin.
Yeah, thank you.
Okay, so this ends the workshop. And so thank you very much, everyone, for coming. And so we can still have some snack and drink. And actually, so the symposium continue. You know, tomorrow there will be a workshop on program verification, if you want to attend it, and still the conference on linguistics, you know, for proofs also.
Thanks, Frederic, for organizing all this.
It's not really an external thing, it's part of So typically, it's going to try, it's going to like give it
And Google would
a
be
pattern, and you can restrict the places.
much more useful if it would.
And it's going to try to unify that against lemma
But I guess
statements.
that's just.
So you can say, for instance, look, like, give me lemma but 0 plus a string, or like, give me all things that are of the form like something times another sun, or things like that. And you will really like, so it's a much more
Recently,
kind of
recently I started, I
don't
use
know,
Google
like, it's a very
again, which is
different kind of search. It's
the
not like by keywords, it's really like,
traditional version.
That's
not what I call the Haskell version.
yeah, I think so.
That's fuzzy search, and this makes such a
Yeah, exactly. So it's
Why you
I
type
think like
searches
having this
and
really, it's just like the eval or whatever query it means. Like instead you have a search one and you can really put things there.
how usable these two are.
So it's because this you are having right now because I mean
No, I mean,
I think
so basically
that
you
the
can,
version is
typically you can
inherently
also have,
differently
like,
implemented
so you
than
can
Haskell.
just give
The
back
Haskell version, I
underscore
think, is just a
patterns,
text search.
like variable names function.
So it's, if I write
you want to have an equality and have something on one side, you want to say the same on the other, so then you can
formatted text search,
you
I
can
don't
give a
think
name,
it
but it's
is
still going to be
actually, I mean,
so
Google
it's
is.
not going to match kind of variable name used because the statement is going to unify the two. It's basically the same sort of machinery that's used by simp to decide which lemmas. Basically the same sort of machinery.
So what do you mean like in basic? Because
Because searching,
Search
like,
for-
and it's a really powerful thing.
For lemma names could be fuzzy searching. So
No,
you could
you have
you
that.
type, but first of all, it could be
And one thing
namespace
that I also
dependent.
really
So if you write
find powerful is that it's very dumb, but
they
you
wouldn't
can
complain
select
about
where this
not
pattern
knowing about
appears,
functor
whether it is
pullback
in
and
the
then
conclusion
suggesting
of this period or the
by category theory don't receive dot functor pullback.
So you can typically the thing that I
So-
might be lots of
is a combination, like I
Yeah,
want
but
this if I create a conclusion.
There are
hypothesis that mention this
there are probably
thing or things like that.
multiple functor
And like
pullbacks, but
once you
not
use
10.
the like hits,
like
like
So in this case, there are two.
each one
There's
has
received dot functor pullback and
or like
received dot
I
functor.
mean, it's like it's really, really efficient.
but still, I mean,
Search, like, I mean, so
Yeah,
sometimes
rip,
the
grep,
return-
and fuzzy search just gives you
the
10
data might
results.
not
All of
be
that.
stated in the reality that
Or